All right, everybody, welcome back. Welcome back. Okay, so we just talked about the RFCs associated with aggregation and subnetting. So let's do a little review and do an example. So remember that a network has a network ID, a broadcast, usually a router associated with it, and then a collection of hosts. When you chop that up, you create subnets. So each subnet then behaves exactly just like a network, and broadcasts are restricted to that subnet. The device used to get between subnets is a router, and all the hosts inside the network share the same IP space. So they're going to be on the same network, right? The same layer 3 network. Only hosts on the subnet now will know each other's MAC address. Even hosts in the classful address space outside of the subnet will not know your MAC addresses. The tricky thing about subnetting, in addition to figuring out how to divide it up, is that you get all these weird network IDs and broadcast addresses that we're not used to seeing. So we're used to those very friendly 0 and 255s. Now we're going to get away from those. So when we start to change the mask, right, we start to do what we call stealing bits. So if you start at the top and you're stealing bits into the host portion, the zeros, that's what happens to the last octet in base 10 numbers, right? So you get 128, 192, 224. If you steal bits back the other way, then you're going from the bottom up and you get 254, 252, 248 first. So in one sense, this chart shows you both how to steal from the host and how to steal from the network portions. And by the way, stealing bits, that's actual language from the RFCs. So each subnet, as I said, behaves exactly like a network. So you've got to have a router to get out, and each subnet has a directed broadcast. The limited broadcast behaves in the same way for that subnet, the subnetwork ID or the network ID for the subnet, and then a particular range of usable and possible host address space. So everything is the same. What's key for us here is that we've got to remember how to do our ANDing. So don't forget that, because easy subnet problems you can do in your head, or you can do that with common patterns. But the way to ensure that you know what you're doing is if you break things out in binary and then do the ANDing. Let's do a quick example for subnetting. So here we've got the 192.168.1.0 network. The host is all zeros in binary, so there'd be 8 zeros on the right hand side. We've got a default mask here of 255, 255, 255, 0, and this means that we have 256 possible addresses, 254 usable once we get rid of the network ID and the broadcast ID, which is .255. And .255 as the broadcast address. The other thing to remember about that is that it has all ones in the host portion. However big your host portion is, when you put all ones in there, that's the broadcast. Now, the simple way to divide this up, let's say we wanted to do 4 subnets. That means that we divide up the space by 4 and we create 64 nodes per subnet, or 62 usable. So there's our classful address space. The new mask, creating 4 possibilities, requires that we steal 2 bits, because there are 4 possibilities in 2 bits. And so our new subnets and our new broadcast addresses would be there. So there's our breaking up of the address space, our 4 subnets. Each one has 64 possible addresses, 0 to 63 in the first case, 64 to 127, 127 to 191, and of course 192 to 255. When we supernet, we're stealing bits the other way. So in that last example, we just stole bits from the host portion. When we supernet or aggregate things together, we're going to go the other way and glom network chunks together. So we're going to take smaller address space and put them into a larger address space. Subnetting or aggregation is used in conjunction with CIDR notation. So that slash notation, the idea of variable length subnet mask, allows us to manipulate this in a wide variety of ways. And on a particular network, you can have all kinds of different subnet mask lengths, as long as it makes sense, as long as logically you take care of all the address space and properly determine how to route to it. important note here, I guess I didn't want to skip over it here. In order to aggregate something together, numerically, they have to be together. So if you're going to aggregate two chunks of address space together, numerically, they must be together. Topologically, from the router's perspective, they better be wired in a way that you can get to them properly as well. So here's a quick example of aggregation, right? So here is that same address space, and we know the classful address space is the 1.0 network. And the range of addresses is 1.0 to 1.255. And we know that because if we did the ANDing on all of those addresses, they would all give us the same result of 192.168.1.0. Now what happens if we steal one bit back the other way? If we steal one bit and instead create a mask of 255.255.254.0. So we change that last bit in the third octet to a 0. What happens? Well, if you start to AND things together, you find out that the range of hosts together on the same network is different now. It's 192.168.0.0 to 192.168.1.255. So instead of 256 possible addresses, it's now 512. What happens if we steal another bit? Well, suddenly that same address space expands to include two more networks, because what we did is we stole 2 bits. How many possibilities are in 2 bits? 4. That means you just supernetted 4 Class C networks together. So now the address space that is the same value when you do all the ANDing is 192.168.0.0 to 192.168.3.255. The problem that CIDR was trying to address from an assignment perspective was trying to conserve the address space by not having to give small networks Class B address space, right? From a routing perspective, what aggregation does is simplifies our routing tables. So if we didn't aggregate at all, and we looked at this particular set of routes, router number 2 here in the middle of this topology would have to have 5 routes on it, and router number 1 would also have to have 5 routes on it, okay? Because all of the routes that are downstream of R2 would be accessed via R2, but we have no mechanism to collapse them all together. Aggregation and summarization gives us that mechanism so we don't have to have so many routes in R1's routing table. Let's see what that means. So if we start off with, this is exactly what I'm talking about. R2 is directly connected to all of those networks. R1 is directly connected to only one of them. The rest of them are static routes that are reached via R2. And then, of course, R1 would probably have a default route facing back towards R1. One of the ways that you know that you can simplify the routes is that if you see that the routes are all accessed via the same point. So they're all accessed via R2 in this case. A real routing table would have the IP address, right? We might be able to take those and aggregate those together in some way because it's 4 routes, and because the address space is continuous, we can aggregate those together using a /22 address space for R1's routing table. So that one static route on the bottom aggregates all of that address space together. So here is an actual routing table from that same topology. The top one is, of course, R2, and R2 has all of the directly connected routes, and then we have the default route. So that's the routing table at the top, R2. R1 would have all of those as static routes. But here what we've got, well, except for the directly connected 172.16 network. But now by stealing 1 bit, we can aggregate 2 networks together and then 2 more networks together to give us those 2 static routes in the bottom of the middle routing table, 192.168.8.0/23 and 10.0/23. Now, if we steal 2 bits, we can put all 4 of them together and have the 192.168.8.0/22 as our routing table entry. So that was an actual topology built in the lab. Now, as I stated earlier, you know, that's not much of a savings, right? We collapsed 4 down into 1, big deal. But if you have a core router or a backbone router on a large corporation, even in data centers, the number of routes can be enormous. So aggregation can help quite a bit in shrinking a routing table and making routing decisions faster. So they're absolutely critical to ensuring that routing tables don't grow without bound and improving the performance of the routers. A lot of routing protocols will auto-summarize. They'll automatically put things together in a routing table. There are some problems if you numerically put routes together and you forget that you have to ensure that the routes actually exist or that the routes can actually be routed from that same point. Then you created problems for the routing tables themselves or for forwarding of traffic. One of the big ones that happens is a section of the address space might be missing. So let's take a quick example. So here I just eliminated the 11 net. Right? It's the exact same topology, except we took that one network away. Now, if I tried to aggregate that again, what the upstream router would do is say, oh, well, the 11 net is aggregated together with all of these other ones, so let's try to get to the 11 net. But of course, that wouldn't. What would happen is R2 would get packets destined for the 11 net and say, I don't have those addresses, so I'm going to send them right back to my default route. So that's a problem. The solution in this particular case is to use something called a null route. And so that's what the routing table would look like there. I can aggregate 8, 9, 10 together, and then I would tell the router that that other smaller address chunk is going to a null route. And that saves us from the routing loop. Doesn't save us from trying to get there, but it saves us from the routing loop. Well, that'll about do it. There's a little technique for handling some of the address space problems associated with aggregation. Next up, what we're going to do is tackle a more complex aggregation topology and talk over some of the issues that we could have there. As always, thanks for watching, thanks for listening, and may your packets always reach their destination.